Hello guys, what's up? So in this video session we're gonna be considering about the waves and oscillations, which is the third unit of the physics syllabus. We didn't consider it earlier, now it's time for us to consider it. So as you can see now, this is kind of having the waves and oscillations, so which is having two parts, the waves and the oscillations. So we're gonna first consider about these waves, and then after we can consider about the oscillation. So if you just consider about the waves, we're gonna kind of going through the wave properties and the types of waves. That means either they are longitudinal or transverse waves. We can categorize them, and we can learn about the lasers and the Doppler effect, occurrence of beat, and finally the resonance, right? So these are the parts we are focusing on with this wave part, right? Okay, so it's gonna be interesting one. Let's proceed. So this theory is being uploaded to the Google Classroom. You can just download it from there, and I have shared with you via WhatsApp. You can just download it, and it's better you could have a hard copy, which means you can just have a printout of this one, so you can have a handheld paper, right? So you can write the things there. It's better you could have a printout. Right now when you are watching this video, if you don't have that, that's fine, totally fine. You can just refer this soft copy and make sure you can you just download it and print it for yourself, right? Okay, let's consider about the waves. So the first problem will be, what is this wave, right? So wave is a way of transferring the energy from one place to another, right? We have considered many cases that we are transferring the energy. For an example, this charger cable, right? You can just plug this one in, right, the phone, and it's getting charged. How? The electrical energy is passing through these wires, right, these conductors. The electrical energy is passing through this wire to the phone, right? And we have considered about another energy, which is the heat. How many ways that the heat energy is transferred? If you can remember, there are three ways, right? What are these three ways? First one is the conduction, second one is the convection, then one is the radiation, right? The conduction, convection, and the radiation. Now there are three ways that the the heat energy is transferred. Likewise, in a wave, that is the transfer of energy from one place to another, right? So depending on this wave transfer, right, we can classify these waves in two types. Either they are mechanical waves or electromagnetic waves. So that way we can how we are classifying like that, it's with the medium that it transfer, right? Where a mechanical wave need a medium to transfer, while the electromagnetic waves do not need any medium for their energy propagation, right? So what are these mechanical waves then? As I told you before, the mechanical waves are the waves which are being generated and transferred when there's a particle medium. There has to be a medium with particles, right? Right now you can hear a sound. How? The sound generated from my throat, right? You know that there are larynx and pharynx and different structures, right? From there this sound is being produced, and that sound is being transferred to the air, and the air particles is taking that energy to the microphone. You can see there's a microphone right here, so that the air between my mouth and the microphone brings up the sound energy to this mic, and then after it amplifies and recording, and there's a different process, right? So you can see a mechanical wave. If it is a mechanical wave, we need a medium for the production, we need a medium for the propagation, both, right? So and if you just compare with the speed of these mechanical waves over this electromagnetic waves, which we can learn very soon, the mechanical waves are very slow compared to the electromagnetic waves. So the examples for the mechanical waves are these sound waves. As I said before, I'm producing a sound here and it is being propagated, so it's a sound wave, it's a mechanical wave. And wave in a stretched string, let's say you have a string and you kind of send a pulse, it goes through the medium, right? In that case it will be a stretched string. And water waves, right? So let's say you drop something to a water bath or something, so in that case it will produce a wave. And I think you all have been to a beach, right? So there also you see the water waves, the waves that have been formed on the water surface. And slinky, right? I think you have seen the slinkies, right? With a like a spring like shape, you can wave it and you can wiggle it back and forth, right? Like guys, that is called a slinky. So those are the examples for mechanical waves. So then we can consider about this electromagnetic waves. So electromagnetic, which means we have an electric field and a magnetic field kind of vibrating together in perpendicular directions. Now let's say this side the electric field goes, then the magnetic field goes perpendicular to that, as you can see in this diagram as well. So this electric field and the magnetic field oscillating together creates a electromagnetic wave. So electromagnetic waves can penetrate, or actually can pass through in a medium or even in the vacuum, right, where there's no particles, right? And they have very huge velocities, like 3 into 10 to the power 8, right, in the vacuum. Wait, is the velocity of the light? Yes. So light is also a electromagnetic wave. We have just considered it, right? When we are discussing about the optics, we kind of limited to, from that electromagnetic spectrum, we limited to the visible light there. So light is a electromagnetic wave. So any electromagnetic wave, not just the visible light, right? Every other electromagnetic waves also propagate in a vacuum at a velocity of 3 into 10 to the power 8. So some examples are given: the gamma rays, the X-rays, right? The radio waves, microwaves, infrared, ultraviolet, right? There are different types of energies, different types of waves that we can arrange in this electromagnetic spectrum, right? So you can see here, this is the electromagnetic spectrum, the rough idea I can have from this. So we have something called wavelength, energy, and the frequency, right? So there are three things we can see here. The energy is there, the wavelength is there, and the frequency is there. You can see starting from this end, we have the shortest wavelength, where you can see very huge frequencies like 10 to the power 24, starting from this gamma rays, right? Before these gamma rays, we have something called cosmic rays. So cosmic rays, then after we have the gamma rays and the X-rays, then we have something called ultraviolet, right? Ultraviolet. So it's better you could remember these things in a order of maybe increasing the frequency or maybe like reducing the wavelength, right? So the gammas have the very least wavelength while having the highest frequency. When you just come here, ultraviolet, you have the frequency about 7 in 10 to the power 14, and afterward you have the violet, right? Ultraviolet, then after we have the violet, if you just go descending order of the frequencies. So then the violet, we have 10 to the power 14 hertz frequency. In other way, if you say that one in the wavelength, that is having around 390 or 400 nanometers of wavelength. Then after we see this visual light or visible light, we say, so that part we can see from our human eye. So that the color, you know, right, these are the rainbow colors, the 7 colors. It's better you could actually, you need to definitely remember this order, either from the frequencies or either from, not all, but at least the 2 edges, right? Starting from the violet, which is having the highest frequency, ends up at the red, which is having the lowest frequency of this visual spectrum, right? So in there, the red light has a frequency of around 4 into 10 to the power 14, and if I say it in the wavelength, it is around 700 nanometers. Actually, you are learning this one for the chemistry as well. if a student follows the chemistry. So this is how you can see the visible light, right? So we have the ultraviolet, then have the violet, right? Then going all the way up to the red, which is increasing the wavelength or decreasing the frequency. Then after the red, you have the infrared, right? Red, then after the infrared. So infrared, we are kind of using in the remote controllers and all. Then we have microwaves, like we do it for the use it for the communication, the 4G, 5G, those are the 3G, those are the microwaves, and also the microwave ovens, right? Again, it's kind of decreasing the frequency. Then after you see the radio waves, having a low frequency, we are using for telecommunication, the radio communication, right? So going below, we have this, I have put some description about each of these waves, the cosmic rays, the cosmic waves, and the gamma waves, the gamma rays, right? For the gamma rays and the X-rays, we call them the ionizing radiations, which are sometimes hazardous, and if used in the controlled condition, we can have different numerous advantages from those gamma rays and the X-rays and all. So ultraviolet light, the UV, we say it's an unionizing radiation that emits from the sun and some artificial sources of we can have. Then after we have the optical waves, or we say the visual light or visible light, varying from 380 to 750 nanometers. Then we have the infrared, right? You can just go through these things, right? A detailed description is given. And ultra high frequencies, we say now the ultra high frequency UHF, right? Use most of the time we use for radio communications and some structural analysis. Now we have this, thereafter we see this radio waves, which we are using for the radio communication. So as I think you have seen, when you just switch to a radio, they say 91.4, 91.8 island wide, right? That says the frequency that they are kind of the band, the frequency band that they are sending their signals. That is said in kilohertz, right? Normally a human or the mammals actually, right? Most of the time, yeah, not the mammals, right? The human can hear a frequency range of varying from 20 to 20,000 hertz or 20 to 20 kilohertz, right? But if it is a radio wave, it's beyond that, the limit that we can hear. The humans can hear around or above like 48,000 or even 9,000, like 98,000, likewise a kilohertz, right? In the kilohertz range, right? Going about 20 kilohertz. Well, I think you heard, you may know that the bats are using very high frequencies, right, to navigate. Maybe the bats could hear the radio frequencies, right? In that case, the bats don't need to bring a radio with them. They can just turn their heads all over and hear to different radio channels. Who knows, right? Okay, so then we can consider about this transverse waves and the longitudinal waves. So how we can categorize them depending on the behavior or the order that these waves occur, right? So first we'll consider about what are these transverse waves. So transverse waves, they are the particles vibrate perpendicular to the direction of the propagation. Now let's say this is the point that the wave has to reach. Now the wave is coming like this, right? The best example is the water waves, right? Like you have seen the water waves, right? When the wave is kind of propagating, the particles in the medium vibrate perpendicular to the direction of the propagation of the wave. Now the wave is propagating this side while the particles moving up and down, right? That is called a transverse waves. So the transverse waves has crests and thrusts, right? The crests are the peaks, which are the thrusts are the valleys, right? So a crest, then a thrust, and a crest, likewise it's going forth, right? So we can define the length of the wave, how far the wave is, by defining something called the wavelength, that is the lambda, right? Lambda is the wavelength. So wavelength here in a transverse wave, we can define it in the two consecutive distance between the thrusts, or the two consecutive distance between the crests, right? Or the crest, the consecutive distance between the two crests, or the thrusts, right? So the examples are these. As I told you, the water waves and waves we can form by like perpendicular excitation of a string. Let's say you have a string like this, and you can just wiggle it back and forth like this, right? Like this. So the wave is being propagated by just perpendicular excitation means that. And the electromagnetic waves, okay. So even though we kind of classify the mechanical waves in transverse and the longitudinal waves, well, we can put that electromagnetic waves also for this classification, kind of overriding, but we can put it to that classification because in an electromagnetic wave they have both this troughs and crests, or the peaks and the valleys, right? For both the electric field and the magnetic field. Okay, remember that. Next we are moving to this longitudinal waves. So longitudinal waves are where the particles kind of moves to the same direction of the wave propagation. The best example is the sound wave, right? If I say like that, right? So what will happen? There will be a compression of air particles, right? The air particles get compressed and form a wave, and that is being propagated front. So if a sound wave or any longitudinal wave that is being transferred, it is transferring with, we call them compressions and rarefaction, right? Compressions and rarefaction. So the particles in the medium where there you can see they are kind of overlapped, or they are kind of concentrated at one point of the wave. We can say them to be compressions, while there's kind of a huge gap between the air particles, we say rarefactions, right? So compressions and rarefactions. So that those are the longitudinal waves. So the particles vibrate parallel to the medium of the propagation of the energy. So this is how we can identify them. We can see that there are these compressions and rarefactions. The examples are the sound waves, the ultrasonic or ultrasound waves, the infrasound waves. Most of the time these longitudinal waves are the sound waves, right? The waves that we are producing by the sound. Okay, then let's learn about the physical parameters. Now eventually we are kind of going deeper, and you know how the physics works, right? Physics is not something that we learn the things qualitatively. We're gonna quantitatively, giving numbers, giving some values, we should able to describe a certain phenomenon or certain incident or a parameter. Now here we are going to learn about what are the physical parameters that are there for that are related for the waves. So first one is this period of a wave, the time period, right? So and we have these are not like foreign terms, because we have considered them for the rotational motion as well, the time period. So time period is basically how long it takes to complete a one cycle, or take a change of 2-5 phase difference. So if you are not familiar with the phase difference, that's fine, right? Don't need to worry about it too much, because we can consider it very soon. So basically you can just remember like time period, or the time that is taken to complete one complete cycle, right? That's a period. And the opposite of that is the frequency. Opposite means kind of having the opposite relationship, right? For the frequency, we can say that is the number of cycles that is occurring, the number of cycles that is occurring within 1 second. So we define the time period in hertz. So this is in hertz. We define the time period in seconds, while the frequency in hertz, right? Hertz means per second. This is in hertz, so that is per second, right? Per second. Hertz is per second. Okay. Then after the wavelength, right? I told you the wavelength is kind of length of the wave, hence the name wavelength, right? So wavelength is the distance between 2 points where the phase difference is kind of 2 pi, right? The phase difference is 2 pi. That means let's say one wave going up and the other wave going down. So there's a difference of pi, right? That means there's 180 difference is there. One wave goes up, one particle, if you consider about a transverse wave, the one particle goes up, the other particle goes down. that is having a difference of 180, right? Then again there will be a chance that you get a particle that is going up. So the distance between the consecutive distance between two of those particles, we say them to be the wavelength, right? Simply, if you just consider about a longitudinal waves, then the wavelength is the distance between two consecutive compressions or two consecutive rarefactions. We can measure the compressions very efficiently than the rarefraction, so we can define the wavelength to be the distance between two compressions if it is a longitudinal wave. But it's a transverse waves like this, so the lambda is the wavelength is the distance between the two consecutive crests or the two consecutive thrusts, hills or valleys, right? That's the wavelength. Okay, then we know something called the amplitude. Amplitude is the how high a particle can reach. Now this is been mostly defined for the transverse waves, which are the particles going up and down, right? So the amplitude is the maximum displacement of the particle from its neutral position, or we say them the middle position. Let's say now if I just consider it here, right, you can see these are the particles that is going up, right? Let's just see like this. So now these particles has reached up to here, the displacement is here, but you can see there's a maximum displacement of the particles, right? The maximum displacement of the particles has gone up to here, right? If I just plot it, now this is the maximum displacement. Now if I plot the displacement s with the time, the displacement of the particle with the time for a transverse waves, now this will be the amplitude, right? This will be the amplitude, the maximum height, the maximum displacement of a particle in the medium when a wave is being transferred in the medium that where it goes perpendicular to the direction of the energy propagation, and that's the maximum displacement it can occur from the center point or from the neutral point, or in other words from the equilibrium point, right? So from that point, what is the maximum displacement? That is will be the amplitude, right? So the maximum displacement of the particle we can obtain from the neutral position when the propagation of wave is called the amplitude. And this is the important thing you should remember. This amplitude is kind of defining how much of energy is there in a mechanical wave, right? So higher the amplitude, higher the energy that the wave has, and the energy of the wave is kind of directly proportional to not just the amplitude square. And this is the only equation that we need. Remember, we are not replacing that one with a constant because that's not there in the syllabus. But we should remember that the energy of a wave is depending on the square of the amplitude, right? So that is called the amplitude. So we are currently at this physical parameters related to the waves. Now we have considered about the time period, frequency, wavelength, amplitude, and finally the velocity of the wave, right? So there's a velocity of these waves, right? There will be a certain velocity of these waves to propagate, right? So the velocity of the wave propagation depends on the medium, if it is passing through a medium. If there's no medium, there won't be the mechanical waves that we can see, but still we can see the electromagnetic waves. That will be the velocity of the electromagnetic waves in vacuum, which is 3 into 10 to the power 8 meters per second, right? So the velocity of the wave, that is the distance traveled by a wave in a unit time, right? That's the obvious definition for the velocity. When there's a certain displacement within a certain time, we can just divide the displacement by the time. That's the displacement per unit time, or the distance traveled with a unit time, that is the velocity. So the velocity depends on, as I said, the velocity depends on the properties of the medium. It's totally depending on the medium, right? Different mediums has different velocities, but we can use this expression, which is V equals F lambda, right? This is something we have used for the optics as well, right? If you just know the velocity we can find out the frequency, or if you just know about the frequency and the lambda, the wavelength, we can just find out the velocity. Likewise, this is a famous equation, right? V equals f lambda. You should remember that, right? The velocity of a wave at any medium, right? Even though there exists a medium or not, we can just apply this equation, V equals f lambda. So depending on the medium, the frequency doesn't change, right? That's the interesting thing, right? So when the mediums are interchanging, the frequency doesn't change. What change will be the velocity by changing the wavelength, right? The frequency is constant. Let's say now it's something we have already considered, right? Let's say there's a torch with a green, let's say yellow light, right? Then you are just, no, I have a torch here, but it's not yellow light, right? It's kind of white, right? So, but let's say it's a yellow light. So just shine it in the air, right? Like this. So you can see that it's the yellow light, right? A yellow color is being projected as the light. So there will be a certain frequency for this yellow light. If you refer the optics note I have given you there. And let's see, let's say if I just shine it through water, which means a different medium, will I get a different color? No, right? The color doesn't change, which means the frequency doesn't change. If I just shine it through water, still I see that one as in the yellow color. But there's a chance of change in the velocity. Yes, there's a change in velocity, thus the wavelength decreases. So remember, when switching between the media, it's just the frequency that is constant and the wavelength and the velocity that is changing. All right, so I told you this wavelength and the velocity, these are kind of dependent on these are depending on the medium, right? So different media has different velocities of the waves, right? So we're gonna consider some of those medias which are there for the A-level syllabus, right? So we're gonna consider the first one, which is the propagation of a transverse waves in a stretched string, right? Transverse waves in a stretched string. Like let's say you have a now I'm just using a wire here, the same charger wire, right? Now what we can do, we can just have a string like this and just pivot it at this end, and you can even pivot it from the other end by stretching it like this. Now it's stretched, right? Then after I can send a wave through this stretched string so that the wave goes like this, right? It goes all the way like this and this, right, to this end. So there will be a transverse wave that we can produce in a stretched string, and that the velocity of that transverse waves we can find out. The velocity of the wave v equals root t over m. T over m. So that is the tension of the string. T is the tension of the string. M is the linear density. M is the linear density where the mass per unit length. Now let's say this is having this cable, let's say this is 2 meters for an example, right? 2 meters and having a mass of 4 kilograms. So 2 meters has a mass of 4 kilograms. 2 meters has a mass of 4 kilograms. Then mass per unit length means we should consider 1 meter of it. Just 1 meter of it. Then what should be the mass? 2 meters, 4 kilograms. Then 1 meter, 2 kilograms, right? So the mass per unit length is 2 kilograms per meter. Okay, that's we say as the linear density even. So you can define it like that. So in this example, or in this scenario, let's see how we can find out the linear density or the mass per unit length. Remember, it's not the mass of the entire string, even though the length, the string is few kilometers long, right? You should consider the mass of the unit length, which is just what's the mass for 1 meter, right? So in case if you can't find it out, we'll see that we can we can follow a different technique, and we can find out the mass per unit length like this, right? If the cross-section area is A and the length here is, let's say, L, and you know that here we are considering 1 meter no mass per unit length, that is 1 meter. So the length will be just 1 meter. So we know that density is equal to mass over volume, rho equals m over v. So mass is equal to m is equal to rho times v, density into volume. Let's say the density of this string is rho and the cross section area is A, and if you are writing the volume, you can write the cross section area into height. So the cross section area is here A, and into height, which is the length here, that is L. That L is 1 meter, since we are considering the mass per unit length, right? So it's the mass per unit length, so we are just considering the 1 meter. Interested in the 1 meter. So instead of the mass per unit length, I can just write A times rho then. Here we have the A and here we have the rho, A times rho. Then we can replace this T equals m over v, this m, the mass per unit length, as A times rho, right? We can just replace it, the A times rho. That's how you can find out. Now should we need to remember this? Yes, we should definitely remember this equation. The velocity of a stretch string, that is root, the root sign is important, right? Root T over M, right? Root T over M, that's how you just find it. In case if you can't find the mass per unit length, but you can find out the cross-section area, and if you know the density of the material that this wire or the string is made, you can just replace that mass per unit length with A times rho, right? So it will be V equals root T over A times rho. All right. Okay, so right now here I have navigated to the questions. So I have extracted them from the Pesuru book. So if you are just having that Pesuru book, you can just turn to the page number 11 in the book 3, right? Book 3, you have the waves and oscillations, and turn to the page number 11 and go to the question. You can see, just go to the question 18. Go to the question 18, right? So that is the two. If you don't have the Pesuru book, I have shared this PDF also to the same Google Classroom, but please don't share it with others, because it's kind of illegal to share, right? Publish it with kind of having keeping an electronic version. So you can just refer it to yourselves, right? Don't share with the others. It's okay, right? You can just share it, but yeah, okay, fine. Anything you can do, right? All right. So yeah, we are going to the 18th question there. So it says something like, when the tension in a guitar string is doubled without changing its length, the frequency of the given tone will, right? Now the guitars, right? They have the strings. Are they? Yes. They are string instruments, right? Like the guitar, violin, the cello, double bass, likewise different string instruments are there where they are using the strings, right? The strings are not they are completely stretched out, right? The strings are completely stretched out, so that will be a stretched string, right? Once you just maybe like here it's a guitar, so once you play the guitar, right? Once you play that string will be vibrating, right? So that vibration will be going as a what kind of a wave? Transverse wave, right? It will be a transverse wave that is being occurred in any string, right? Not just guitar string, any string. You can see that it is creating a transverse wave. Okay, now asking that when the tension of the guitar string is doubled, which means the tension is doubling. So once how we can find out the velocity of the wave through a transverse waves through a stretch string? Well, by V equals root T O M, right? Root T O M. So given in this question, what we do, we just double the tension, which means we are just doubling this tension without changing the length. So if the length changes, there might be a chance this mass per unit volume, mass per unit length could change, because If you just stretch it, it will kind of, stretching means you may reduce the cross section area, right? But here it says we are not changing the length, instead we are just only increasing the tension of it. Alright, so we have to find what happens to the frequency of it, right? It's not just asking about the velocity, it's asking about the frequency. What happens to the frequency? Well, we can just write like this way, right? Since we know that, let me just go to the question. We know that V equals F lambda. We know that V equals F lambda, where V is the velocity of the wave, F is the frequency, while lambda is the wavelength, right? So from that one, we can see that velocity is proportional to the frequency, right? When the frequency increases, also the velocity could increase. But the velocity of a stretched string can write root T over M. Since the velocity is proportional to the frequency and the velocity is equal to root T over M, I can just write like this way even. Velocity is proportional to root T, right? When the tension increases, the velocity of the wave, velocity of the transverse waves in a stretched string will be increasing as form of the rule, right? Then I can just write the root T that is proportional to the F, because velocity is proportional to the root of the tension and the velocity is proportional to the frequency of the frequency that is being produced. Then I can just write like this way. So what is doing there, the string, the tension of the guitar string will be doubled. So if I write F dash, that will be 2 times T, right? So what factor that is been the new frequency will be changing? Is it by the root? Is it by the 2? No, right? It should be increasing because it's now there's a direct proportionality. It should increase. When the tension increases, the frequency should increase. What factor? Yeah, it should increase by a factor of 2. So the answer has to be 3, increase by a factor of root 2. Got it? So that is how we can just find out. We can apply this scenario. We can apply this equation for a certain question, right? If you know the tension of the string, if you know the mass per unit length, or in other words, if you know the cross-section area and the density, you can use either this equation or maybe the other one, right? Maybe you can use this equation and find the like the wave, the velocity of the wave through a stretched string. Alright, next we are moving to the velocity of sound. The longitudinal wave, right? The sound wave is a longitudinal wave, as we discussed earlier. So velocity of sound in air, right? When you have the air, right now I'm surrounded with air, otherwise I can't breathe, right? So now there's a wave, that is the sound wave, that is propagating from my mouth to the microphone. Let's just see what is the velocity of this wave propagation, right? So the velocity of a sound wave is equals to root gamma p over rho. Root gamma p over rho. What is the P? P is the pressure, the surrounding pressure. Right now I'm in the atmospheric pressure, right? Could be lesser than your case, because you know when you go up, the atmospheric pressure kind of drops, right? We are kind of closer to the sea level, but I'm kind of above the sea level right now. So could be a different air pressure, the pressure in the atmosphere, but we can just apply, right? Any place you can just apply the pressure of the current air, which is the atmosphere here, and rho is the density of the air. Yeah, we can define a density for the air as well. How do we define the density? We just consider in this space, I can consider 1 meter length, 1 meter breadth, and 1 meter height cube, right? Imaginary cube, and that's the 1 unit volume, right? That's the unit volume, and I can measure the mass of the air that I can enclosure, right? I can collect for that 1 cubic meter volume, then that will be the density of the air, right? Density, it's just the mass divided by volume. So this density of the air is the rho. What is this gamma? Well, Gamma is the ratio between specific heat capacity of the air. Specific heat capacity. Have we considered that one for the heat? Have we finished the lesson heat or the thermal physics? Yes, guys. What is this specific heat capacity? If you kind of not remember, it's time to pause the video and go through the note about the specific heat capacities. We have learned this one for the second law of thermodynamics. Second law of thermodynamics. There are two specific heat capacities for the air. One is the specific heat capacity at constant pressure, which we write as Cp, and one is the specific heat capacity at constant volume, Cv. Okay, make sure you pause this video right now and go to the note. If you can't remember, right, go to the note, refer this specific heat capacity at constant pressure and specific heat capacity at constant volume, and just come back. Okay, I hope you referred the note. If you can't remember it, right now we'll just check. Yes, there are two capacities, specific heat capacities. One is the specific heat capacity at constant pressure, where you are keeping a constant pressure, then you are expanding the system to maintain that constant pressure. That means you should increase the volume. So the supplied heat will be the supplied heat, the Q, delta Q, right? Delta Q will be increasing the volume, which means doing a work, P times delta V, and also it is increasing the internal energy, delta U, of the system. So for the specific heat capacity at constant pressure has to be higher than the specific heat capacity at constant volume. Then the gamma is the Cp over Cv. I think that there also we have just considered the same gamma, right? That's Cp over Cv, right? That's around 1.8, but it differs with the air that we are using, right? The quality of the air. So that will be given if you are asked to calculate a certain value, the certain velocity, using this equation. So gamma is basically the ratio between the two specific heat capacities. See, since we have done the heat, now it's a cashew, right? You can just understand it very easily. Cp over Cv, right? Then remember this. Should we need to remember? Yes, definitely you should remember how we can find the velocity of the sound in, or basically the longitudinal wave in air, right? Then we can just consider we know the very famous equation PV equals nRT, no? Then you can apply that one. Then PV equals nRT. Instead of N, we can put M over M, right? This is what we can normally do, right? So my intention is to replace this P and rho, right? P and rho. So what I can do, I can just apply P equals nRT, so it will be like this, and instead of the N, which is the number of moles, right, N, I can just put M over M, simple M, which is the mass over the molecular mass. So I can just shift this M to this side, and I can take this V to downwards, right? Just cross multiplying it, you can just take this V to the downwards. So you have M over V, M over V. M over V is what? Mass divided by volume. Sounds familiar? Yes, it is the density, right? Mass divided by volume is the density. So density of the air sample, we can just write the mass of the air sample divided by the volume of the considered air sample. We can get it, we can derive it from the PV equals nRT equation, the ideal gas equation we say. Then this one is the rho. Then I can just take that rho, the entire thing, to down again. So I can have the P over rho, that is to be RT over M. R is the universal gas constant. T is the absolute temperature, the temperature right now, and measured in Kelvin, right? Not in degrees Celsius. And M is the molecular mass. So instead of P and rho, I can replace P over rho is equal to RT over M. So the gamma is equals to RT over M. So if in a case like you don't know the pressure, but you know about the absolute temperature right now, the absolute temperature of the considered movement, and R is the universal gas constant, which is 8.314 joules per mole per Kelvin, right? Over molecular mass, that is the molecular weight of the air sample, right? Then we'll just go through what are the factors that determine the velocity of air. Now we know that it is the pressure or the density, and we using the pre equals nRT, we can even derive it as RT over M. Now you can see first parameter will be this pressure and the density. Since the density increases relative to the pressure, what happens? What will happen if you just increase the pressure of a system? When you need to increase the pressure of a air system, right, gaseous system, we can increase the pressure by reducing the volume. Increase the pressure by reducing the volume. So it's like this. Now let's say this is the certain syringe or something, right? Now this has a certain pressure. This has a certain pressure. Let's say it is P naught, and it has certain density. The mass is M, and we have volume of V naught. How do you write the density then? Pressure is P naught. Then you write the density. Density is equals mass divided by volume. Volume is V naught. M over V naught. Right? To increase the pressure, what we can do, we can just reduce the volume. Reduce the volume of the sample up to here. Let's say the new volume is V1, right? So the pressure increases to P1. When you have that volume reduced, the pressure increased to P1. And if I write the density, if I just consider the density is equal to, now it is rho over V1. Now we can see the volume reduced. When you reduce the volume, what happens to density? Density increases, right? So that's what it says. Since the density increases relative to the pressure, when you need to increase the pressure, you can reduce the volume. When you reduce the volume, the density also increases. So if I just consider the ratio between the pressure and the density, if you need to increase the pressure, the volume has to reduce so that the density also increases. So this one increases, this also increases. So overall, the P over rho factor remain constant. So there's no change in the velocity when the pressure and density changes, right? We can consider the current velocity of the sound by multiplying, like taking the root and the gamma, the current pressure over the density of the air sample. But if you need to change the pressure, the way we can do it is either we can introduce some mass, then also the density increases, or else we can reduce the volume. That way also the density increases. So both pressure and density increases. If one increases over the other, let's say this keeping the density constant, if the pressure increases, then there will be a significant change in the velocity. But the pressure and the density both are increasing at the same time, so there won't be an effect on that. But what about the temperature? Yeah, since velocity is equals to gamma RT over M, where the gamma is these things, right? So gamma is a constant for air, R is the universal gas constant, which is a constant again. M is a constant for a gas sample, right? If you're not changing the composition, the overall, the mean molecular weight is a constant value. Then there's a significant difference we can obtain when you are changing the temperature, right? So we can write like this. You can just write here V is proportional to, if you have the tube, you can just write it down. Therefore the V is proportional to root T. Then I can compare the case with two scenarios, right? If the velocity is V1, then the temperature will be T1. If I just increase or decrease the temperature, that will be the T2. Then the new velocity will be proportional to V2, that is proportional to the root T2. Have a like you can just divide 1 by 2 or something, then you can have like this, right? So if you just know the temperature at one case and the velocity at one case, you asked to find the velocity at another case when they are given the temperature, you can use this relationship, right? How this is being derived from this equation, V equals gamma RT over M. How that gamma RT came? From the PV equals nRT, because velocity of a sound is equals to root gamma P over O. Alright. Then the molecular mass, right? Yeah, you can see the molecular mass also plays a certain role in determining the velocity of air. Velocity of sound in the air, right? Then when the molecular mass increases, the velocity decreases. Yes, you can see that there's a direct not a direct proportionality. There will be an inverse proportionality here. V is proportional to 1 over root m. So when the root m increases, the molecular mass increases, the velocity decreases. All right. So this is kind of a common question that is being asked for most of the time for the MCQs, but the students kind of mix it because of thinking it wrong, right? So what happens? The question is, what happens when you like have a wet air, which means a humid air? It could be a misty day, right? What can you say about the velocity of the sound? Now for an example, let me just consider it like this way. Now we have a certain environment where it is completely dry, and you have it's completely dry, so you have a certain molecular weight of the air, right? You have a certain molecular weight. Now when it is kind of humid, or let's say it's a misty day, so it is wet, so let's say different m dash or something. Now it's kind of having a humidity, that means it's kind of having more water particles, right? So the question is whether this m is greater than m dash or m is lesser than m dash. That means the molecular mass of the dry air, the mean molecular mass of the dry air, is whether it is higher than the molecular mass of the wet air, where we can see more water molecules. Think about a second and come up with an answer. Yes. Okay. Right. So this is the dry air. So a dry air is consisting of hydrogen, carbon dioxide, water, right? H2O and nitrogen, right? Everything, right? So if you just consider about these molecular weights, hydrogen we have like 2, right? Hydrogen we have 2, and water we have 18 grams per mole, and nitrogen that is 14, and 14 that is around 28 grams per mole, right? Then the carbon dioxide, carbon is having 12, and this is oxygen 16, so 16 into 16, that is 32, and that 12 altogether 44 grams per mole, right? Different molecular weights are there, right? So if you just have a mean value, you can see some are even going to 44. The carbon dioxide is around 44 grams per mole, and it is 28. This is 2. Likewise, now the helium is also there. There are different methane, different types of gases are there. Now if you just consider the molecular mass of dry air, you should consider these all, and you should have a mean value. But let's say you have a wet condition, like a humid condition, where you have more water molecules. If there's more water molecules, this environment is kind of consisting most of the time with water which is having 18 grams per mole 18 grams per mole of yes 18 grams per mole of molecular weight, molecular mass, right? So if I just take the mean value there, you don't see much carbon dioxide, you don't see much hydrogen and nitrogen, all the things, but you see most of the time you see the water vapors like this. So the mean molecular mass drops, right? We kind of having the idea, okay, the water molecules should be higher in the mass, so they kind of, now the molecular weight increases, right? This should increases, but it's not, guys. Remember this one. If you have a humid condition or misty day, you have more water molecules than in a normal condition. So when you just consider the dry air, it is kind of the mean value of all the air, all the types of molecules that we can find out. In here we have, most of the time we have the for most you can see the water molecules which drops, right, which drops the molecular mass. So what can you say when the molecular mass drops? The velocity of the air increases, right? The velocity of the air increases. Let's say now these I have even, now when I'm at the childhood, I have even practically tried these, right? And actually I have practically experienced this. Let's say two people are kind of at top of two mountains like this, right? So one people is kind of shouting the other person, right? Let's say he's kind of a certain distance apart, right? Let's say 500 or 1 kilometer, right? You can do these things because it's a hilly area this day, right? This area, so you can just climb to any mountain and you can shout it, right? No one blames, and right, it will be interesting. Right, so what you can do, you can just shout it from a mountain, and there will be a certain, after a certain time, the person at the other mountain can hear this the sound that I have sent him, right? If it is a misty day, or maybe it's kind of almost rained and just stopped, or maybe it's about to rain, right? In these conditions, we have more water vapors in the atmosphere, right? In a scenario like that, if I shout, the person can hear much faster. I mean, if it took, let's say 2 seconds or 3 seconds or 3 seconds to reach this sound in a dry day, it will be a kind of reducing up to 1 second, or most of the time he can within a very short time period the other person can hear the voice. Why? Because the velocity of the air increases when it is kind of having water molecules. Okay, remember guys, the velocity of the wave, velocity of the sound is changing with the molecular mass, the quality of the air as well. Then the next thing is the wind, the final thing. When you have the wind for the support, right? Let's say you just shout something to the air, and if the wind is to the same direction, what happens? The velocity of the particles that is moving forward, that compression and air fraction is moving forward, will be added that velocity. So when you have a wind towards the same direction where the wave is being propagated, it will be kind of increasing the velocity, and it is to the opposite direction, the velocity will decrease, right? That's how you just can find out the velocity of the air, the longitudinal wave, not the velocity of the air, the longitudinal wave, which means the sound wave through air propagate. Alright guys, so now we'll consider a question from that one. So currently I am at the spacer books, and book number 3, question number 13, right? And as I said you before, I have shared you this PDF as well. You can just have a printout of it if you don't have the pacer books, right? So again, you might be wondering why I'm just referring to these books. So right now, since we have a limited time, it's better we could do the past papers along with the theories that we discussed, because we might not get a chance to do these questions if we do the other questions. But that's fine. We can refer any book, right? The objective physics books I have shared with you, so you can refer to that as well. Right, so currently we're gonna do the fourth question and the third one, right? We'll do the third one first, and then after we do the fourth question. Okay, what you can just pause the video right now, and you can try these two questions, and yeah, you can resume, right? All right, so I think you did those two questions, right? I'm just not waiting the time so that it will kind of increase the video, right? The length of the video. So that's why I'm not just kind of not waiting for you to do. So what you can do, you can just pause the video and do the question, and you can resume the play. All right, so we are trying the second question now. If the velocity of the sound in air at 0 degrees Celsius is V0, the temperature at which the velocity becomes 2V0, right? So let me just grab this one for the whiteboard, and we can just do those two questions. Let me just have a screenshot and a sketchbook. All right, so new speech sketchbook we are opening up for the waves. Right, okay. Okay, so let me just paste the question here. Right, if you couldn't see the question properly with my the face and all in the side in the screen, you can just refer this question now, and even you can pause the video now and you can just try it, right? Okay, so I'm just going to discuss the second question. So if the velocity of sound in the air at 0 degrees Celsius was V0, how we just find it when it is at when it becomes 2V0, what's the temperature? So I can just write, so V is equals to root gamma RT over M. That means V is proportional to the root T, right? Here it's the absolute temperature, so I can just write V0 when it is at 0 degrees Celsius, so 0 plus 273, right? Then when it becomes 2V, right, 2V0, that will be a different T. So it is given in degrees Celsius, that's why I'm just adding this 273 and so on. So here also I can just add 273 to make it Kelvin. So I can just divide. That's what we did, right? So last time, like in the note, you can see that V1 over V2 is equal to root T1 over T2. You can just use this expression simply by dividing the two proportionalities. So I'm gonna divide 2 by 1, so it will be 2V0 over V0. That's plus 273 over just 273, right? So V0 cancels off, and there's a square root so that we can square it. So it will be 4 equals T plus 273 over 273. So pretty straightforward simplification. I can just cross multiply this 273 to this side, so it will be 4 times 273 equals T plus 273. So 273 can go to the other side, then it will be 4 times 273 minus 273, which will be T is equal to 3 times 273, right? I'm just saving the time because it's an MCQ, very old one, but kind of can apply, right? So it is 3 times 273, so it will be 9 here. Then 3 times 7 is 121, so it will be 2. Then 6 and 2, that is 8. Alright, I see the answer to be the fourth one, 8, 19. Alright, so if you see the second one, which means the fourth one, which is not at 0 degrees Celsius, it is at 27 degrees Celsius, but it is 7, that would be the V. When it becomes 2V, right? You can use the same trick here. So you should get V1 over V2. If you can remember, if you are using this equation, you can do like that. So it is, let's say V1 is V, V2 is the thing we should, V2 is 2, let's say. Or maybe I can just write it like this. Yeah, okay, fine. I'll just write like this. So it'll be V1, that is V, V2 is to be the 2V, that is here it's 27 plus 273, which is 300, right? I can just straight away write 270. Okay, let me just write it like that. Okay, fine. So this is the T in degrees Celsius plus 273. Okay, again the 2 cancels off. I can write 1 over 4, that is equals to 300 over T plus 273. So this goes up and this goes like this. Then it will be 1200 1200 subtract 273, right? T equals 1200 minus 273, just cross multiplying it, right? And just subtracting or taking this 273 to the other side. Then T is equals to, yeah, the subtraction of 1200 minus 273, so it will be 7 here. Okay, this should be the answer 4. Let's see. Here 9, 2. Here we have 11. Yes, 9. As expected, right? That's how you just do. If you just you are certain with the answer, you can just find 1 or 2 digits and you can just underline it, but make sure you just find the full answer, right? So this is 927 degrees Celsius. Fine. So we'll just go again the node and we'll proceed with the theory. Okay, the next one is the longitudinal wave in a metal rod, right? When you have a longitudinal wave in a metal rod, longitudinal waves are, let's say you tap from this side, then the wave is propagating as not like a transverse waves. It will be like propagating in compressions and rarefactions, right? If you can't remember, just pause the video and just drag the video backwards and see where we have discussed about these longitudinal waves. So longitudinal waves of a metal rod, you can see V equals root Young's modulus divided by the density of the metal. Wait, Young's modulus? Sounds familiar? Yes, guys. Now you might be thinking why I'm doing this one. Why I'm doing this the waves and oscillations at kind of the end of this syllabus, right? Because you might need to encounter some constants and some sort of theories that we need to learn before, and we can discuss this one very easily then. Young's modulus we have discussed is for the elasticity, where at the Hooke's law stress equals, yeah, right, Young's modulus times the strain. So stress is the F over A, that is equals to Young's modulus, which is a constant, and E over L, right, elongation over the natural length. Okay, there are the Young's modulus. Why we are using to the same expression, V equals Young's modulus over rho. Rho is the density of the metal, and for this one we'll just try this question. We'll go to there's something called longitudinal waves, and for this we're gonna try the 16th question. You can try the 16th question. Now it's this at the 17th page if you have that page of the book. So the 16th question, which is the 2019 past paper MCQ question. Okay, just pause the video right now and try the question, and then after we'll discuss. Okay, so I think you paused it and you tried it. Let's discuss it. Right, a composite rod is formed by connecting two rods A and B as shown in the figure. Okay, now there are two rods. Longitudinal wave of velocities in the rod A and B are 3,210 meters per second and 6,420 meters per second. It's twice, right? You can see the numerics. They are kind of the velocity at the B is twice than the velocity of A. Respectively, a longitudinal pulse is applied to the free end of the rod A, propagates with a wavelength of 2 meters. What is the wavelength of this wave when it is propagated through the B? Okay. Now we have two rods to consider, the A and B. Now we'll first focus on the A, right? So the thing here is we are given the velocity and the wavelength also given. The 2 meters per second, the wavelength also given. What's the parameter we don't know? That's the frequency. So can't we just find the frequency? Yes, we can. What's the equation we can apply? V equals F lambda, right? So it's said to be 3,210, right? You can see they are kind of having very large velocities, but not compared with the electromagnetic waves that is having 3 into 10 to the power 8 meters per second in the vacuum. Okay, so it is 3,210, that's the velocity, that is equal to frequency. We don't know that one yet, and the lambda is given to be 2. The wavelength is 2 meters. So I can have the frequency, that is that's 12, and it is 1605 hertz. Okay dokie, so I got the frequency here of this pulse. Let's say it's a pulse that is going, right? Pulse means a single wavefront, right? We are not just continuously tapping on that the end of this rod A. We just tap it once and that wave is propagating through the system of rods. Now we found the frequency of that one to be 1605 hertz. Then the similar wave, the same wavefront or the pulse we say, enters to the rod B. Okay, so do we know the velocity there? Yes. Do we know the frequency there? Well, I told you, when it is changing from one medium to another. Why we say it's one medium to another? Well, if you can remember, we have considered the similar thing for the optics, right? Let's say a wave, a light that is coming through one medium have a different velocity. When it is entered into another medium, it has a different velocity. That's why it kind of bends, right? It bends towards the normal or bends away the normal, right? So here, that's why when they have different velocities, that means they are different medium, right? Now here you can see two media. One is this A and the other one is the B. Even though it's the same, kind of seems like the same rod, but have two media with different speeds, right? It could be the Young's modulus that is changing. We know that V equals root Young's modulus over O. Could be the Young's modulus or could be the density that could change by changing these two. We can change the velocity of the longitudinal wave. Okay, so we have the velocity here, that is 6,000. This one, right? 6,000. This, that is equals to F lambda. So what's the frequency? This one. So how do we get the like you can just substitute here like 1,600 and 0.5. Let me just do like this. It's 3,210 divided by 2. That's how we got this value into lambda. So this is again 4. Sorry, this is 2, right? It's twice of this, and this 2 multiplies, then lambda is equal to 4 meters. piece of cake, right? Actually, you don't need to involve with this the Young's modulus and the density here. I can just basically calculate by this, right? Okay. All right. Then we are trying this question, right? Then we are trying this question, which is the question number 15, kind of summarizing of two theories that we have already learned. And this is the year that I wrote the A-levels as well, 2015. All right, just give it a try. Pause the video right now and just give it a try. All right, guys, so let's try the question number 15 then. So it says a wire of radius 1 millimeter made of radius 1 millimeter is made of a material of Young's modulus 4 into 10 to the power 11 newtons per square meter. Yeah, that's the units of this Young's modulus, is subjected to a tension of 30 newtons. The magnitude of the ratio VL over VT of the longitudinal wave velocity over the transverse wave velocity. Okay. Now, if a wire that is subjected to a certain tension, that's acting like a stretch string, right? Let's say the same charger wire that I'm taking right now, right? If I just stretch it like this, right? If I just stretch it like this, so I can send a transverse wave, and similarly I can send a longitudinal as well, right? A longitudinal wave as well. So there might be a vibration that is going along the wire with that compressions and rarefactions, and also we can create a transverse waves as well. So here it's asking the ratio between those two. So how we can just get it? It's like this. I felt it. All right. So yeah, let me just grab the question to the board. Okay. Right. So in this case, we should know how we can find out how we can write the equations for the longitudinal wave and a transverse wave, right? So longitudinal wave, if it is a rod, the longitudinal wave, we can write VL, that is to be the very recent theory that we have discussed. That is, we can just get it by this one, right? Young's modulus over rho. Okay, let me just write, that is root Young's modulus over rho. Then how do we write the transverse wave, VT? The transverse wave we have already considered. If it is a stretched string, that is root T over M, root T over M. So if here you can see now it's not given the mass per unit volume. Sorry, mass per unit length is not given, right? But instead we are given a radius. Then we can find out the area. So if you just replace this M with that A times rho, I can just write that one with T over A times rho, right? We have discussed this theory earlier. Then now we can have a certain idea, because this is also rho, this is also rho. We are asked to find the VL over VT, right? The ratio between those two. Yeah, can we have it? Yes, we can, right? So this will be then a Young's modulus over rho. Then the rho is the density of the material, and times so it will be the VT down. That means root T over that arrow. We can just flip them up, because I just need to take the reciprocal of it. So it will be A times rho over the T, right? You might be if you are wondering how I can get it. Well, it's like this. So VL over VT, that is equals to, I just write in smaller, Young's modulus over rho, the entire thing root, over the T over A rho, entire thing root, right? That's how I just wrote it like this way. So you can see there's this root sign is there, root rho and root rho, that cancels off. So we can have VL over VT that is root Young's modulus A over T. So do we know the Young's modulus? Yes, we know that. That is 4 into 10 to the power 11, that is given like that. And the radius is given, and we are asked to take the pi to be 3. So how we can write the cross-section area? That's, remember, it's the radius, so not the diameter. So we can just straight away apply it. The cross-section area is pi r squared. So pi will be 3. R squared will be 1 into 10 to the power minus 3 squared. Why I wrote it like that? Because it is given in millimeters, so I have converted to meters and squared it. Over the tension of the string is also given, that is 30. Okay, so that 3 and this one cancels off, and I can just cancel off this one. Then it will be 10, right? 10 to the power 10. Then I have 4 and 10 to the power 10, which will be 2 and 10 to the power 5, and taking the root afterward. So here it is 10 to the power minus 3 squared, which will be 10 to the power minus 3. So what we get will be then 10 to the power 2, which is 200. The ratio will be the 200. The answer has to be the 3. Alright guys, so let's move forward with the other theory that we can learn now. We have considered about the longitudinal wave in a metal rod. Then after, we can see the transverse wave on a liquid surface. We can call them the water waves, right? Any liquid, we can see the waves are being propagated, right? So that is kind of depending on the gravitational acceleration and the depth, right? So let's see now, if I just draw it with a certain ocean, let's say I'm just drawing the seabed of the ocean and kind of coming to the coast like this, right? So now the waves are like this, and now this is, let's, oh sorry, I have switched the auto correction mode. Okay, it's like this. Okay, all right, so actually it has to be the other way. Let me just, okay, now you can see, now this is now how we can write the velocity of the wave, velocity of the water wave. V is equal to root gh, where g is the gravitational acceleration, h is the depth. Now here we have a depth of h1, let's say. Now here we have a depth of h2, right? Now what can you say about the velocity here and the velocity here? Which should have the highest velocity? Yes. Now since the h is higher here, the depth is higher, the velocity of the wave will be higher. The velocity of the wave will be that the wave will be traveling very faster in the deep ocean than the shallow sea, right? The shallow ocean near to the coast. So you can see here the v1, since the h1 is kind of greater than the h2, and the v is proportional to the h, root of h, right? So it will be the v1 that should be higher than the v2. Either way, we can get the velocity of a transverse wave. That means the waves kind of going like this, right? On any liquid surface to be root gh. All right, so we'll do a question on that as well. Okay, for this one we're gonna try the question number 24, which is given for the 2011 A levels for the new syllabus, right? The figure shown here is a shape of a tsunami wave, right? Tsunami wave of wavelength lambda and amplitude a, right? Wavelength lambda and the amplitude a reaching the beach. The speed of the wave can be approximately given by v equals root gd, where d is the depth, right? G is the depth of the sea. When the wave reaches the beach, okay, I think you have heard about this tsunami, right? and we also experienced this tsunami 2004, right? So at that time, whenever you see a tsunami wave, it's a transverse wave, right? It will be a transverse wave occurring on a liquid surface. Here is the ocean. So it's also given the same equation, right? Root GH or root GD, where D is the depth. Here it's the H we have considered about the depth, right? So the figure shows shape of a tsunami wave. You can see that now even the diagram that I have drawn also, I have drawn it something like that, right? Let's see what's happening there, right? Let me explain the phenomenon of this tsunami. Well, now there will be an earthquake. We can consider about the earthquakes later in this session. I mean, not in this session, but overall in these waves and oscillations. So let's say there's an earthquake that is that occurred in the depth of the ocean, right? At a certain depth of the ocean. Then there will be a wave that is being created, and that wave will be transferred through the liquid surface. Now, once the ocean is kind of having like in the deep sea, the velocity will be higher, right? The velocity will be higher, and we know that V equals F lambda. And I told you the frequency always depending on the source. Source means the one who creates the sound or one who creates the wave, right? Let's say now this is the earthquake. Now there will be a certain wave that is creating with a certain frequency. That frequency will be constant. But when you go now in the deep sea, the velocity is very high. It's having a very huge value because we know that once the depth is higher, the velocity will be higher. When you have a higher depth, since the frequency is a constant, what can you say about the lambda? The wavelength? The wavelength will be higher. You can see here, if I just mark it over here, the wavelength is this much, right? Around this much. So if the wavelength is higher, wavelength is what? The length of the wave. If the wavelength is higher, what can you say about the energy of the wave? The energy, now you know that wave is a way of propagating the energy, right? Here the energy that is released out from that earthquake is being transferred over this liquid surface, the ocean surface, right? Then what we can see here is, since the wavelength is larger, the energy of the wave is distributed over a large area, right? Over a large distance. Let's say now we have 20,000 joules. If that 20,000 joules will be distributed over 2 kilometers or something, right? It has to be, right? The wavelength is very large here because of the higher velocity, right? Let's say 2 kilometers, that means 2 into 10 to the power 3. This one cancels off, so it will be like 40 joules, right? 40 joules per meter, right? The energy is distributed over very large surface, very large distance. But what happens when it is approaching to the coastal area? When the wave is approaching to the coastal area, the H reduces, the depth reduces, right? When the depth reduces, what happens? V equals root GH. So what happens when the depth reduces? Then the velocity reduces. When the velocity reduces, V equals F lambda. Frequency is a constant, so when the velocity of the wave reduces, the lambda reduces. Now you can see the lambda is kind of this much, right? Approximately that much. So that what happens? The length of the wave reduces. Then what happens to that energy of the wave? Well, it was kind of distributed over large length or large distance when the wavelength is larger. But now the wavelength is getting smaller and smaller. Then the energy that was there in the wave get scattered to or get concentrated to a shorter length. Then what happens? The amplitude, if you can remember, the energy of a wave is depending on the amplitude. Higher the amplitude, higher the energy, right? Then once the energy is getting scattered or concentrated to a shorter wavelength, the amplitudes get bigger, right? The amplitudes get bigger. So you don't see a very huge wave of water that is at the deep sea. But once that wave reaches to the ground or reaches to the coastal areas, depth reduces, velocity reduces, lambda reduces. So a large amount of energy is being concentrated to a shorter wavelength, so the amplitudes will be higher. Then this wave, this height of the wave could go up to 3 or 4 meters, or even like going 10 meters, right? A 10 meter of wave could form closer to the coastal areas, rushing out all the buildings and the constructions, the trees and everything, right? The habitats, everything, destroying, because the amplitude of that water wave is very large, right? So during a tsunami time, now those days in the Sri Lanka also we didn't have a tsunami warning system. Nowadays we have them, right? So it takes couple of hours to reach this tsunami wave to a coastal area. Within that time, now they can have the ability to give a warning, so that the people here, the coastal areas, can evacuate, right? So we're gonna go in detail about the tsunami waves, and there are you can see plenty of questions. The past paper questions are being asked for the previous years. We'll just go through them after we discuss about the earthquakes, right? We're gonna learn about the earthquakes and all. There we'll learn about how these earthquakes are generated and how they are being transferred, how we can classify them, and finally the tsunami, right? So here I gave you a certain description about it to answer this question, right? Now let's go through. The figure shows the shape of a tsunami wave of wavelength lambda, amplitude a, reaching the beach. The speed of the wave can be approximately given by this equation, okay, where it is the depth of the sea. When the wave reaches the beach, what happens? Lambda should decrease, right? The wavelength is decreasing. Then the amplitude should increase. Wavelength decrease with the decreasing velocity. Then the amplitude increases. So you can see lambda and wavelength, the lambda and velocity, the velocity decreases and the amplitude increases. The answer should be then the second one, right? Yes. All right, so that's how you can find them out, right? Now we're gonna go to discuss about the properties of waves, different properties of waves, right? Now the waves are showing some properties or some behaviors, right? Let's see what are the behaviors or the properties exhibited by these waves. So the wave shows the reflection. Reflection. Is it light? Yes, actually the light is also a type of a wave, right? Electromagnetic wave. Wave, then after we can classify it to a sound or light, right? So yes, the sound and the light both. And not only just the sound and light, right? All the waves shows these types of properties. So if a certain physical parameter shows these properties, we can classify them as waves. What are they? They show reflection. Yes, for the light we have considered it, how the reflection happens, and the refraction. Yeah, refraction also we have considered, and some more things we can consider. That's diffraction, interference, and polarization. So there are altogether 5 properties that a wave exhibit. We'll go through eventually what are these properties. Right? We have a rough idea about this reflection and refraction. We'll consider about this diffraction, interference, and polarization in deep. Okay, so the reflection is ability to return back to the same medium at interface, right? Interface between the two media. Now we have an interface. If you have an interface, now the wave can go in and without penetrating into, the wave can reflecting back to the same media. And the refraction, right? The ability to enter to the second medium through the interface. You know that refraction, right? When it is enter into the second medium, it kind of bend towards that. If you can construct a normal, it bends towards the normal if it is a rarer medium. If it is a denser medium and falling from a rarer medium, you know about it, right? We have considered them for the light. That's why we did that lesson before this, right? And the diffraction, that's something new. So that is called the ability to bend at the obstacle. If you have a obstacle, the light can, or any wave can bend and go through the missing that obstacle, right? Just bend it over there at the obstacle and it can move forward. And the interference is the ability to superposition of the waves, right? When you have a couple of waves, right, when you have, let's say, more than just one wave, we can add them and we can impose them. So we can say them superimpose or superposition, right? Then the final one is the polarization. That means we can extract the wave from one plane if they are vibrating at different planes, right? Let's say one wave is going like this while the other wave is going like this, right? It could be like occurring to different directions, but we can extract the waves that are coming to one plane. That is called the polarization, right? Okay. Now we'll just consider each of these behaviors using a stretched string. Now let's say you have a stretched string that is stretched, right? Then we'll see how we can demonstrate these properties. Okay, first one is the reflection, right? I told you the reflection is it's kind of very cold here, that's why I'm about to sneeze. Sorry. The reflection is it doesn't go to the second medium. It is getting transferred back to its original medium when like they meet an interface or something, right? A boundary that is kind of stopping the wave, right? So here we gonna, now if it is a stretched string, we know that we can produce longitudinal waves and also the transverse waves, right? In last question we kind of considered it, but the most significant or the prominent one here will be the transverse waves, right? In a stretched string, like irrespective of like it to be any kind of a string, right? You can just produce transverse waves easily than longitudinal waves, but it doesn't imply that there's no longitudinal waves at all, but the significant one here will be the transverse waves. Okay, so that what we can do here for demonstrating the reflection. Now let me just grab the same charger wire. Okay, so now let's say this is a what we call as the rigid, or maybe a certain wall that we can connect this wire, right? Now this is the wall that the wire or the string has connected, and what we can do, we have a certain tension here. There has to be a certain tension, right? Then we can send just one pulse like this, right? Just one pulse like this, so it goes all the way up to here, right? Then what will happen, we can see the reflection in two ways, right? There are two types of reflections that we can see. One is this rigid reflection and the other one is the soft reflection. Two kinds of reflection. Okay, so how we can see the rigid reflection? Let's say a string is rigidly attached to a barrier, so no vibration can occur at the point on that string, right? So let's say you send a pulse. This is called the incident wave pulse. Pulse means just one wave front, right? You're not just continually sending a wave, just one wave that we have sent. So it is going along the wire, right, and comes to this point. Now this point is kind of firmly fixed, right? It's rigidly fixed, so that this particle can't move up or down, right? At the very end, which is the attached point, the particles there can't move up or down. Then what will happen? It is a rigid case, right? It's a rigid position, so we can see a rigid reflection where the wave flips down, and it flips down and get reflected back, right? So we can say the phase difference is pi. Phase difference is pi. Okay, so which means it has flipped down 180 degrees, right? So the phase difference is 180 degrees. Now this is the incident pulse, this is the reflected pulse. That is for the soft rigid reflection. So the next one is the soft reflection. So when you have a soft reflection, what will happen? Now the same incident pulse we are sending, but here we have a soft connection. How do you make a soft connection? Let's say you have a rod here and there's a ring here, right? You can have a ring there, and for the ring you can just attach that string. Then once you wave it, give it a wave pulse, the wave pulse will come along the wire, and at this point where it is connected to a ring, then the ring can also go up and comes back down, right? So in that case it will be a soft point here. It's not rigidly connected, it will be a soft point that it can also go up and down, right? With the ring it can go up and down along this the attachment, right? It could be a wire or a pole or something that the ring has placed in the middle, right? So what will happen, this particle, the particle at the very end of this wire also can go up, unlike the previous case, right? Then it can also go up and down. That will be a soft reflection. So there won't be a phase difference, right? Actually I misspelled it. Just correct this one, not phase, it is phase, right? This phase, there's no phase difference. The phase difference is 0, right? It's not turning down, just go forward and comes back, right? That is called the reflection, right? That's the reflection. So reflection we can demonstrate in two ways, the rigid reflection and the soft reflection. Where you have a rigid point, it's connected rigidly, so it will be a rigid reflection, you see a phase difference. And this is a soft reflection where we have a soft connection. Okay, with that knowledge we can do a past paper question. So currently we can just go to this one, right? You can do a couple of questions here, right? Let me just let me just first consider about this one, right? The sixth question that is from 2000. A transverse wave pulse is traveling on a stretched string as shown in the figure. The left end of the string is tied to a light ring that could slide on a frictionless rod perpendicular to the string. Thus, reflected pulse is best represented by. Pause the video and think about it. Okay, I think you paused the video and thought about it and you have an answer. Let's see now. What type of a reflection is this one? It's a soft reflection, right? It's a soft reflection where you can see this side is kind of softly connected. Then there won't be a phase difference. The shape should be same as that, but kind of turning to this side, right? Why it is turning to this side? Because first this part of the wave is approaching, and that is the one that should reflect back first, right? And this part is the one reaching to this point after the first portion reached, right? Then it has to reflect at the back, so it will be something like this. First this part reached, so that part has to go like this. It's not flipping down, there's no phase difference, right? Because it's a soft reflection. And thereafter you should see this one. So the best representation will be this one, right? The second one. First one cannot be because first it's not this part that is being reflected, right? This part is the one reaching to the reflection, right? Subject into the reflection, this part, and thereafter you see this part, right? So the answer has to be the second one. Okay, so there are a couple of examples you can try now. You can have the ninth one as well. Yeah, so shall we do this ninth one? Okay, so before we try this ninth one, let's do this, right? Let's do this one, the first question, which is from 1992. I think you are at the previous life, right? Let's try that question. Yeah, a composite string which consists of two parts A, B and BC with different mass per unit length is stretched as given to a certain tension, right? The mass per unit length AB is much smaller than BC. Now the BC is kind of a rope that is having a higher mass than the AB, right? BC is having the highest mass, the mass per unit length, than the AB. Now what matters this? That is affecting for the velocity, right? Velocity, we know that velocity of a transverse wave going through a string is root T over M, right? Root T over M. So when the mass per unit length is higher, the velocity decreases because there's an inverse proportionality. It is for the denominator, so when the mass per unit length increases, the velocity should decrease, right? It should decrease, right? So we'll see here the mass per unit length is at mass per unit of AB is lesser than BC. Now what can you say about the velocity here? The velocity, let's say V1, that V1 has to be higher than the V2, right? Because here mass per unit length is higher, so the velocity will be lesser, right? Actually you can demonstrate this one like for the when we are going to schools, we did these demonstrations and all, right, with a heavy rope and a light string. Yeah, let's see. Now the pulse is sent like this. Now it started from A and goes along up to the B. It goes along up to the B. Then now we are asked to find the resulting pulse and the strike like, right? How it should be. Now you see that there are two pulses. Each of this answer, they have given two pulses. Now we have just sent one pulse. Why there are two? Okay, to answer that, we should have the idea, like if you can remember, we considered something for the, we can consider the same scenario for the optics. Right? We have considered it for the optics. Let's say now this is a certain interface where you have water or something at below, right? Let's say we have water or something here, and we have this interface, right? Let's say a certain light is being incident to this interface with a certain angle, like this, right? I. Now you know that it get refracted in, right? It get refracted in, and a part of the light that will be get partially reflected, like this. There will be a total internal reflection as well. If you can't remember that, just go through it. There will be a refraction, right? There will be a refraction. Why there's a refraction? Because the velocities are different. Here in this medium you have a certain velocity, we call them the rarer medium. this medium you will have a certain velocity, that will be the denser medium. So the light here is traveling to the rarer medium to the denser medium, which is subject into a refraction. Okay, the similar thing that is happening in here as well in this question, right? Now you can see the velocities are different. Which will be the highest velocity? Here, this one. So AB string is like a rarer medium, while the BC string is like a denser medium. So you can see a refraction, and also there could be a partial reflection. All right. So I told you I mentioned the word refraction. We already know it. That's the second property of these waves. Okay. So we'll go through this part and we'll come back to that question and try to answer it. So refraction is the when you have two velocities, you can the propagation of wave from one medium to another medium, we say that the refraction. So how we can have two velocities, right? Two velocities, or basically construct two medium from the same stretched string. Similar to the question given, we can have a heavy string and a light string. Now in this case, it is given a heavy string and a light string connected like this. Now this is the incident pulse. Now the pulse is coming all the way up to the boundary, right? All the way up to the boundary. Now we have a heavy string. After this point, we have the heavy string. Now once the wave pulse propagating like this, it kind of easily displaced the particles in that wave, right? Particles in the medium, particles in that stretched string easily when you have a light string, right? Now the wave can easily lift up the particles in the light string. But once they reach here, now they find that heavy string, right? Heavy string. So the wave has to lift up the heavy string kind of hard, right? It won't be an easy task, but it should, when the wave is propagating forward, it should somehow lift up the particles in the heavy string as well. So there will be a portion of the wave that is being transferred to the heavy string and goes to the same direction. But the particles here at the interface experience a certain reflection as well. Why? Because now they are kind of very hard. They are kind of lifting up the particles at this end, at the heavy string, right? So there will be a reflection, and that will be a what? That will be kind of like a rigid reflection. Why? Are these particles go very smoothly and very without any effort? The particles at the heavy string also goes up? No, right? It will be kind of the wave coming from the light string sees this point as a kind of a rigid point, right? While they are lifting up a little the particles at the heavy string, there will be a reflection, a partial reflection as well. So you can see something like this goes back, right? What happens the other way? Now you can see there's a phase difference of 180 degrees because of it is a rigid reflection. Now this is the refracted wave pulse, this is the reflected wave pulse, right? You can just note it down here. This is the partially reflected wave pulse, partially reflected wave pulse, right? So what happens if the other way? What if the incident wave is coming from the heavy string? Yes, when now the heavy string is coming, the wave is coming through the heavy string like this and reaching to this interface where you see the boundary of or the junction of the heavy string and the light string. Now it was even coming very hard, right? Pulling out all the particles in that heavy string, heavy rope. And once they reach here, once the wave reach here, it can easily transfer to the light string, right? So there will be a transfer which is called the refraction. Similar to that, there will be a partial reflection here. But can the particles at here move kind of freely? Yes, right? Unlike the rigid reflection, if it is a rigid reflection, the particles here actually they feels like they can't move up, and that's why there's a phase difference and the reflection will be there. But if it is a soft reflection, the particles at here at the very end also can go up and down, right? So that is why there will be a soft reflection. The same thing happens here. There will be a soft reflection from this point. The particles at here, because it's a light string now, so the light string or the string that is having the lesser mass can easily displace up the particles there when the wave is propagating through. So there will be a reflection here. This is called partially reflected wave pulse, right? So there will be a partial reflection there as well, but that is a soft reflection. That is a soft reflection, right? That thing is given here, right? Within this like paragraph, I have mentioned how this is being happen. Okay, so this is the partial reflection, and that is a hard reflection, or we say that a rigid reflection. This is a soft reflection happening here, and there's this refraction also can be seen, right? So then we'll answer this question, what's happening here. Now it's a light string and a heavier string. Now we can pause the video, process it, and come back. Think about an answer. You can just go through this part again and come up with the answer. Right? Got the answer? Should be something like this, right? Now at here, there will be a rigid partial reflection. So the wave will be flipped down. The wave will be flipped down and goes to the same direction to the A. While there will be a certain refraction happening here, and the same wave front should pass towards the C, right? So which is the most suitable answer? That has to be the second one, right? It has to be the second one, like this. All right. Now with that thing, now we saw that the reflection and the refraction. Now we'll just consider about the diffraction. Diffraction is the bending of the wave when there's an obstacle. Well, from a stretched string, you can't just demonstrate it clearly, or we can just specifically demonstrate the diffraction from a stretched string, right? So we'll see another method that we can observe this diffraction, and we're gonna learn what is this diffraction in detail, right, in there. Okay, next one is this interference. So the interference is kind of we can combine or join two waves, and we can impose them, or we can just add them or subtract them, right? Basically we can just have a combined, or we can have an equivalent wave when you have two or more than two waves, right? Yes. So to study this interference, what we can do, we need to learn about this principle of superposition, right? Principle of wave superposition. So it's like this, right? When the total displacement of these particles resulting by the propagation of waves through several medium is equal to the algebraic sum of all the displacement caused by each wave. Now let's say we have a couple of waves that is coming towards the same direction, let's say, right? Then they get imposed, or they get kind of mixed at the middle, right, at a certain point, and the total displacement of a particle in the medium is the addition of the algebraic addition of, or algebraic summation of the displacement creates by, or the caused by, each wave. Now for an example, you can see here in this first example, both waves are coming facing together like this, right? Facing together, and both waves are coming up like this. Then what will happen? Once they get like combined, right? Once they get superimposed here, what happens? The amplitude, now this is having a certain amplitude, let's say, This is also having a certain amplitude. Amplitude is the maximum displacement of the particle from the neutral position or the middle position, right? So if the both waves are kind of going to the same direction, I mean both waves are having the same phase difference, or in here also the wave try to go up, displace up the particles in the material. Let's say that stretched string, right? Let's say the particles here also trying to go up, and the other wave that I'm sending, that also kind of trying to go up, the particles trying to go up, right? Then what happens, they meet together, then it creates a wave pulse having a higher amplitude. The opposite scenario you can see when you have something like this, right? When you just have something like this, when one wave try to go displace the particle up while the other wave try to displace the particle down, once they come together, the net displacement will be 0. So the first part, for the first thing, we can call them as the constructive interference. The constructive interference, where there will be a construction, right? Like it's the getting added, right? Then we can write the constructive interference. When there's no phase difference, we say them synchronized waves, right? The two waves are kind of synchronized, so they are having the same phase. In that case, we can have the amplitude of the superimposed wave to be the A plus B. Let's say one wave is having the amplitude A, the other wave having the amplitude B. So you can just add them together. Then the superimposed wave has an amplitude of A plus B. We call them constructive interference, right? Remember that word, constructive interference. And the other one, the destructive interference, that we can see when the phase difference is 180 degrees. One wave is trying to go up, the other wave is trying to go down. So when you just combine them together, you have an amplitude of a diminished amplitude, right? A reduced amplitude, A minus B. You can have the modulus there, which means you can just consider about the magnitude only. You don't need to write it minus or plus, right? Here we are basically like having an idea of what will be the magnitude there. That will be the subtraction, right? If it is a constructive interference, we can have the addition, where in a destructive interference, we should subtract the waves. Why? Because one wave is trying to go up, the other wave is trying to go down. But in this case, right, even though the amplitude reduces, it doesn't destroy the total energy, right? It doesn't destroy the total energy. Now we know that we already heard that okay, the energy of a wave is depending on the amplitude square. But what if the amplitude reduces? Will it destroy the energy? No, right? The energy is there within this the same wave, but the amplitude will be lesser there. Okay. Then the fifth one, the polarization. Polarization is the separation of wave existing in one plane, existing in many planes. If you could extract the vibration or the wave in a one plane, we can, that's called the polarization, right? So what we can do here, we can have a cardboard or something with a hole, right? A rectangular hole there, and we can have a wave that is going like this. If the rectangular wave, the rectangular hole will be towards the vertical, what happens to the wave that is coming out? Will there be a wave coming out? No, right? This wave the wave pulse get hit by this cardboard, and there won't be a wave propagating to the other side. You don't see a wave from this side, right? Which means I can filter out the waves that are coming vertical direction. Now, if the waves are coming vertical direction, that can penetrate through that, actually not penetration, that can pass through that hole, right? The rectangular hole. But if the wave is kind of like this, it won't pass through that rectangular hole, right? That is called the polarization. Now we can extract the waves that are coming from different planes. We can extract the waves that is coming from one plane, right? We can detect it to be coming from one plane. It's not like no, let's say one wave is like this and the other one is propagating like this. We are not just like folding them and adding them, right? It's basically just extracting the waves at one plane. When there's a wave that is having different planes, right? Vibrating at different planes. Okay. Right, so that's what you can do when you are gonna define when you're gonna demonstrate the polarization from a stretched string, right? Then let's go to the next one, that is called the ripple tank, right? Ripple tank. This is an interesting one, right? The ripple tank. You can demonstrate all these 5 properties. Now we have considered about 5 properties now, 5 properties of waves: the reflection, refraction, diffraction, interference, and polarization. All these 5 properties you can see, you can observe, demonstrate through this ripple tank, right? It's very interesting if you kind of like if you can do this practical at schools, because at that time you are kind of covering up the entire lab, right? You make the lab kind of darker there, and then thereafter you're gonna observe these patterns, right? It's very interesting one, the ripple tank. The ripple tank is a very simple device that we can construct, right? It's not very deep one, a shallow water tank, right? A shallow water tank with a glass base, right? There will be a glass at the for the base, right? And it's not like the fish tank, right, that you have seen. Very shallow one, like this. If I draw a cross section, I mean if you see it from a side, it will be just a tank like this. And well, very shallow one, it will be just 1 or 2 centimeters, 2 centimeter height, and we're gonna fill up with that one with water, right? Can fill that one with water. So kind of a diagram is given in the tute as well. So this is called that the tank, right? The tank. So we're gonna have some ripples there, hence the name ripple tank, right? We're gonna have some ripples. How we can make the ripples? Well, there's a certain sheet, right? A vibrating sheet is there, and that is connected to a motor, and that is being suspended by 2 rubber bands. Then it be like this, right? I'll just draw it here. It's something like this. Now this is that if I draw it 3D, this is that sheet that goes up and down. How that thing goes up and down? Well, there's a motor here, right? Just a motor here, and an unbalanced wheel is there. There's an unbalanced wheel like this. Now it's fixed at here, right? So you have this is the similar mechanism that you can see for the vibrating motors, right? If your phone vibrates, there's a vibrate motor there having the same mechanism. It's not like the motor that is connected to the very center of a certain mass, right? A certain dial or a disc. It's a kind of a heavy disc, but it's not connected to center, somewhere at the end. So when this one is vibrating, when this one is rotating, there will be a vibration that is formed. Since this sheet is being suspended by rubber bands, this can vibrate up and down, right, with that rotation of the motor. And this is being rotated, that creates a vibration, and that vibration will be transferred to this sheet, and the sheet is kind of softly suspending because it's not rigidly connected. It can vibrate up and down. So with that, it creates a wave or ripple in this water in the tank, right? So that we can name it as the ripple tank. So you can see these structures are there, and we have a lamp house or a lamp that is on top of it, right? So you can just go through this paragraph, right? And then after you can see the vibration of the sheet, right? The vibration of the sheet. Vibrating the sheet, we can have what? Linear wave fronts. These are called linear wave fronts. Like this, it's kind of linear, right? It's going like this. And I told you this is a glass sheet, and in the below we have a screen. Below we have a screen, and we have projected some light. Right? There's a light, a parallel beam of light being produced down. Then it construct, right? It creates some brighter lines here. Some brighter lines on the screen. How these are being creating that brighter lines? Well, I can see it like this, right? You can just draw it here. This is how this bright light is being made. Now let's say this is that water surface. Okay, you can just draw it here, but let me just draw it in the board. Okay, now let's say this is that tank. This is the tank, and this is the wave that is, let's say these are the ripples that is being made, right? Now the parallel light rays are reaching from that lamp house. Lamp house means it's kind of an arrangement of the light that can produce a parallel beam, right? Now let's say the parallel beams are falling to the water surface like this, right? Okay, they are being fallen to the water surface like this, right? So at this part, it's the thickness of the water here, the medium here is larger. So these guys are acting like a what kind of a shape is this? They are acting like a concave mirror. Sorry, convex lenses, right? These are acting like a convex lens. Then what will happen? If it is a convex lens, that means they are converging, right? If it is a convex lens, they are converging the light. Okay, so these are being converging the light to one single point, thus creating a sharp, bright line corresponding to a crest, right? This is a crest, we know, right? This is a transverse wave, so we have the crests and the thrusts. So these are being focused to a single point, creating a bright line, right? It will be creating a bright line like this. While in here, right, we have a trough, right? So this is being again, you don't see a brightness, considered brightness when you have a trough like this. That also will be kind of scattered for another crest like this, right? There will be a certain amount of light that will be falling down, but it won't be brighter as a crest, right? This light, the ray can fall down here, but they are not concentrated to a single point. So we have some bright regions and some dark regions, right? These are the bright regions, right? Bright regions, and there are some darker regions in the middle between two bright regions. So each bright region corresponds to a certain crest on the ripple, right? You can just sketch it there, right? Sketch this one. You can just pause the video and sketch this one in the tube here, right? There has a little space provided, so you can just sketch it there, right? I'll just leave it here. Pause the video and you can just draw it, right? Okay, then now how we can find out the lambda then? Is there an easy way to find the lambda? Yes, that is why we are projecting the light to a screen. And when you have the bright lines, the consecutive distance between the two bright lines, we can say them the lambda, right? You can just easily measure the lambda of the wave that we can construct. All right, Then what we can do, instead of this linear wavefront, we can just consider some circular wave. We can construct the circular wavefronts by replacing this vibrating sheet, right? This vibrating sheet with a single tip, right? You can just have a single tip, and that is going up and down. Then that will construct a circular wavefronts like this. This will create a circular wavefront, like spreading out from the middle point, from the source, spreading out circular. So the bright lines will be showing a circular wavefronts, right? So that we can construct a wave, right? That's how we can construct a wave or construct a pulse. Here we can't just construct a single pulse, right? Most of the time it will be a continuous wave that we are constructing. So those are the two types of wave that we can see. Now let's use this ripple tank for the demonstration of the 5 properties of the waves, right? So we're gonna demonstrate the reflection, refraction, and we can even demonstrate the diffraction, the interference, right? Yeah, those things we can demonstrate. Okay, let's first see how we can do the reflection, how we can demonstrate the reflection, right? So for the reflection to occur, we know we need to have a rigid or maybe a certain surface that prevents the wave to be propagated into the other side. Yeah, for this one, what we can have a wall. It could be a piece of wood or maybe a piece of glass that is having a higher thickness, right? If I see it from this cross section like this, I can have a wall here, right? A wall here. Then what will happen? I can place something like this. Then it will kind of hit on this wall and get reflected back. That you can see from a ripple tank, right? Then the refraction, right? Reflection is something you can easily understand, right? What about the refraction? Yeah, for the refraction to occur, we need to have at least two media. How we can construct a different medium in the same tank of water? Think about it. When you have two medium, that means the velocities are the one changing, right? You should have two velocities. How we can have two velocities when you have a certain water sample? Well, we know the velocity is depending on velocity. We can find out the velocity of the water or maybe any other liquid on the surface, the velocity of a wave, that is equal to root gh. V equals root gh. H is the height, right? If you could change the height of this medium, then what we can do? We can have a different medium. For that, we can place a glass slab at a certain region, right? When you have a glass slab, now this is having the depth of h1. Now the water is having a depth of h2, right? So V is equal to root gh. When the h decreases, the velocity decreases. So the decreasing velocity means it's like a denser medium, right? When the velocity is higher, we can consider it as a rarer medium. When the velocity is lower, we can consider that as a denser medium. Now the wave is going from the rarer medium to the denser medium. Now we have constructed or obtained a denser medium where the velocity is lower by making the height of the depth of the ripple tank shallow, right? Like this. By putting a glass slab, you can have that medium, a denser medium there. Okay, then what we can do, that's what given in here. right? This is done by placing a thick glass plate on the top of the tank. Top of the tank means we are placing it at the bottom, on top of the tank, right? Then you can see here the same scenario that we have considered for the refraction. Now if I just can construct a normal like this, now the wave is coming like this and bends towards the normal and goes through the medium. You can see now these are called the bright lines, which are corresponding to the crests, right? So the distance between two adjacent bright lines, we can call it as the lambda. This is the lambda, right? What happens when the velocity reduces? V equals f lambda, right? When the velocity reduces, the lambda also should reduce. You can see here the lambda is reduced, right? Now here it is having a higher wavelength, while here it is having a lower wavelength, right? So we have applied a Snell's law for the light, right? So light is also a type of wave. So can't we just apply it here? Yes, we can. So that Snell's law is, it said the sine value of the incident angle and the refracted angle is a constant. Yes, it is. Here we can write sine I over sine r, that is equal to v1 over v2, the velocities of the two media, the ratio of the velocity of two media. And since v equals f lambda, I can write f times lambda 1 and f times lambda 2. I told you the frequency doesn't change, it depends on the source. Whatever the frequency it produces at the source will be propagated into the media. So the f's can cancel off, that will be the lambda 1 over lambda 2. Right? You can find out the incident angle and the refracted angle if you just know these parameters, or the other way, right? You can just play with them. You can find out the wavelength here, the lambda 1 and the lambda 2, right? How do you find the lambda? Well, you can just find it from the screen, right? Now there are some bright lines that will be propagating to the like not propagating, actually they are kind of projected to the screen, some bright lines. So you can just find out the lambda by just measuring it from a ruler or something, right? Okay, then that is how the refraction is happening. Then we have the diffraction, right? Diffraction. Now I told you the diffraction is the bending of light through bending of a wave when you have an obstacle. When you have an obstacle, the wave tends to bend. We'll see how this diffraction can be demonstrated from this ripple tank. Okay, so let's see about this diffraction. So when there's a certain obstruction, right? When there's a certain barrier there, the waves are trying to bend, right? So you can see here. Now this is a hole. This is a hole that is made lesser than the lambda, right? I can see here this is the lambda. Let me mark the wavelength here. This is the lambda, and if it's, let's say this is the space between the gap between the two poles. If this d is lesser than lambda, what you can see now, the circular wave, the linear wave fronts, these are the linear wave fronts, right? The linear wave fronts completely turn into circular wave fronts. The linear wave fronts completely turn into circular wave fronts. While in here, this is kinds of the lambdas but you can see here there's something interesting happening. Now whatever the lambda that you got here, right, the same lambda can be seen in here, right? It is not changing the frequency or not changing the lambda. In that case, it's not changing it shouldn't change the velocity, right? Yeah, you can see that there's no two medium, right? It's just the same medium, but the bending of the wave that we can see. So the lambdas are the same if it is the wavelengths are the same if even though it's a circular wavefront or a linear wavefront, whatever it is, lambda is the same, but the arrangement is kind of different. Now it's turning the circular wavefronts to linear wavefronts. Now if we just consider here this one, now here in this case it is kind of a lambda and the the lambda and this space, the d, they seems to be equal, right? The lambda and the wavelength of the wave, the linear wavefront, and also the space that is there between these two walls kind of seems to be the same. So still it creates some of the bending, and here you can see now the space is even kind of bigger than the lambda. There's a little little curve shape is there. How that curve shape comes, that's due to the bending of light. You can see now if it is like going perfectly straight line like this, they are not going like that, right? Even though you have a sufficient space to go, the ends of this wavefront, the two ends of the upper end and the lower end of these wavefronts that I'm showing right now, right, this end and this end, tends to bend a little bit, right? Bend a little bit towards the wall, right? Or towards we say an obstacle, right? So in this scenario, when there's a obstacle line, it's not a hole like structure like this, it's not an opening. Basically you have kept a single wall or single object here, right? When the object is lesser than the thickness of the object is lesser than the wavelength, then it won't bend. But when the size of the object is equal or higher than the wavelength, then you can see that still they are kind of bending near the they are bending near these kinds of obstacles, right? That is called the diffraction. And finally we can consider about the interference, right? Interference, we got to know that there are this constructive interference and destructive interference, right? So when we can see this interference when you have two wavefronts, right? So you can see this S1 and S2 are the two wavefronts, and they are kind of making circular wavefronts. These are the two sources, and they are creating circular wavefronts. So you can see here the S1 is producing these kinds of waves, and the S2 is producing these waves, right? Then they get overlap at a certain point. When they are overlapping, when you have two crusts together, it creates a constructive interference. While when you have a crusts and a troughs, right? You have a crust and a trough, or simply we have a hill or mountain and a valley, right? Then if they are combined together, or if they are kind of superimposed, we can have a destructive interference, where one wave trying to move the particle up, the other wave trying to pull the particle down. In that case it will be destructive interference. So just see this one carefully. In these lines, right, these straight lines without the dotted ones, the plain lines, you can see if you just consider the S2 source, there will be a peak here, right? A crest is there. And if you just consider the S1 also we have the a crest there. S2 also we have a crest there. S1 also we can have a crest there, right? Just go with the waves and you can see that. So two crests join together creates a constructive interference. So you can see these lines we have the constructive interference, while the dotted line you see destructive interference, right? Then that is how we can see the interference from a ripple tank. Now there's a simulation on this ripple tank, right? There's a simulation. You can just scan this QR. In case if you have printed this one up, you can just scan and go to this scan this QR and you can go to the same link, right? Let's go to that link, and let me just open it in a new tab, and let's see how we can simulate the ripple tank. Okay, so this is kinds of the simulation that you can have for the ripple tank, right? So don't get hypnotized, right? These lines, So this is how actually you can see from this screen as well, right? You can, if you see through the, if you kind of observe it from this screen, you can still see kind of the waves that are propagating, like, and they are moving forward. So in order to see these waves kind of freeze. Now in this simulation, what we can do, you can just tick on this, then it gets stopped, right? So we can see the moving wave that is kind of similar to like a wave that is freezed, right? The wave that is not moving with the help of this stroboscope, right? So stroboscope is something that we can have, like it's like a fan, right? So there are two ways that we can do it. One is this, there's a certain fan like structure, right? So and each and every segment you have a little hole that we can see through, right? So if you kind of rotate this stroboscope at the same frequency, now there's a rotational frequency we can adjust now. So if this one is rotating with the same frequency of this wave generated, right, that means now you first see the wave pattern, and then after it closes your eyes, right? This one segment closes your eyes. Then after, once it open, what happened? The entire wave fronts, the entire set of waves has moved 180 degrees forward, right? That's how we get the next frequency, right? Frequency means kind of, if you have the same frequency, that means that the period of time will also be the same, right? In that case, if you now if you see through the stroboscope, it closes your eye for a moment, and with that time the wave fronts going one step forward, right? The wave front that is here goes in front, right? The wave that was behind also goes front, right? Likewise, each and every, the wave front will go a distance by a lambda, right? Because you know that it is the time period, the time period of this wave and the time period of the stroboscope we have matched. So in that case, once it passed our eyes, then a new set of wave came, and a gap of lambda being passed. Then if you again watch the wave pattern, and again it closes, right? I mean, it is kind of rotating, so it again closes our eyes. Then again it opens when it is again moved when the waves are moved a distance of lambda again. So when you see through this stroboscope, you feel like the waves are kind of stationary, right? They are not moving, right? It's just flicking up, right? That is what we say as the stroboscope. And how we can use that one is by observing through it. It closes our eyes for a time period of t, and then opens, then closes, then open. Then we can see that the waves that are moving forward on the screen kind of freeze there, so that we can keep a ruler there and we can measure the wavelength, right? That's one way. So nowadays we have a stroboscope like just a flashing of light, right? Now the entire, let's say the entire room is dark and it is kind of flashing, right? It's flashing. You can adjust the flashing speed or the flashing frequency that is kind of matching with this frequency. So in that case, it turns off and turns on, turns off and turns on at the same frequency. So still then we can see that the wave fronts are kind of freezed, right? So you can see here in this simulation, these are the planar wave fronts. You can just select it from here. Either you need plane wave fronts, right? Or maybe this is the plane waves, or you can just make it a single source, that is a circular wave front, right? Okay, let's just see the first thing, which is now here in this scenario, I'm gonna just do I'm gonna add a wall to here, right? Let me just add the wall to here. Now you can see the lights are bent in there, right? Again, don't get hypnotized with this, right? The light rays, not the light rays, but the waves are kind of bent in there, right? If I just reduce the size of it, there will be a certain reflection, right? There will be a certain reflection and all. Then after, you can see now the the thing that is going up will be the reflection, right, and get superimposed with this. And this is the wave. You can see it's kind of bending. Next I'm gonna do, let me just okay, now let me add a slit to here. Slit means again opening like this. Let me just open this one up a little bit. Okay, like this, right? You can see, let me just clear the waves and see it again. I can see here these are kind of like planar wavefronts, right? The plane wavefronts or linear wavefronts now turn into circular wavefronts. You can see here, right? Then we'll just see about that superimposition and all, right? So in that we'll just okay, so we'll make it now this is a single circular wavefront that is being produced. Now I'm gonna have two sources like this, right? But you can see in this can see now these are kind of faded, right? You can see some faded lines that are extending outwards, right? There you see these are kind of the constructive interference, while the black ones are the destructive interference. Now if I just take it out like this you can see now the constructive and destructive interferences. So the black ones are the destructive interference, while the shiny or maybe the color ones are the constructive interference, right? You can just play with this. There are some thing called damping and source frequency. We can increase the source frequency, right, which means the number of cycles per second, and you can just reduce it all the way down, right? Now this is just 3 hertz. Likewise you can just play with that, and you can add anything to there, like the cavity, parabola, anything. And there are some sources, triple slits, obstacle, and likewise you can play with anything with that, right? So going back to this one, right, now I think you should be okay with the ripple tank as well. Okay, so afterward we have the lasers, right? We have the lasers, but we'll just do it in the next video session, right? About the lasers and how they are working and the principle and all, right? Okay, so you can have a little break, and meanwhile I will share you the next video very soon, right? Hopefully today. Then we can go through about the lasers and what are the actions of laser and so on, right? Then we have to discuss about the Doppler effect. All right, so see you in the next video. Thank you for joining this session. Bye guys.